Thank you very much. Thanks for the invitation and the opportunity to talk at GERAD. I was there about 7 years ago with others, Miguel and so on. And so the work here is a little bit related to that. It's in this area of taking equilibrium problems, which are hard to solve, and making them harder. That's the business of what we're trying to do here. I believe it has a lot of interesting applications, some of which we've been explored in papers in transportation and energy and so on. But I think there's a huge opportunity here. So can everybody see my screen? It's with the two screens at once. Hopefully it's good. So overview is I want to motivate this. Why are we even studying this? And then very short review of complementarity problems for those people that have never seen them. They generalize many problems in optimization, zero finding problems, econometrics. You can mix all kinds of things together. It's a very large class of problems. And then what about the discretely constrained, usually integer or binary constrained problems? How do you define that? And then there's this really cool function. It's I didn't come up with it. It's from some of the work, I think, by B. Curtis Eves in the 70s and others to try and take the equilibrium problem, express it as a zero finding problem, but it's a non-smooth function, right? And anyway, it's this thing called the median function when you specialize it to this case. So, and then we have a formulation with binary variables. And then a few colleagues, Martin Schmidt and Marina Leal, some of you may know them, they said, can we get rid of the binary variables? And the answer is yes. And that was the follow-up paper, continuous variable formulations. Computationally, in some ways better, some ways not. But anyway, you can do it in multiple ways. Then I'll talk about some selected results that we have and then kind of next steps and so on. So feel free to interrupt if you like at any time. This particular talk is based on these two papers. This one using the median function, it's in optimization and engineering. And then the follow-up paper, as I mentioned, with my colleagues, Marina and Martin, is in computers and operations research, a continuous variable reformulation. And then there's a whole bunch of other works in the references that I'll talk about. So, why do we study these problems? Well, we're basically taking integer or binary restrictions to problems that involve autonomous agents that are making their decisions by themselves, which are expressed as an equilibrium problem. So if you think of drivers on a road network, they're making their decisions independently, but then there's sort of the price of anarchy that happens. If anybody has been caught in a traffic jam, you certainly understand the price of anarchy. But maybe there's a way to sort of guide things in a way that's a little bit better in an equity sense or other logic senses. And that's where this work fits in. So it's basically allowing for autonomy in these infrastructure networks or supply chains, energy transportation, but throwing on top of that some logic constraints or distributional constraints or design variables, or for example, multi-sector coupling in power and gas and heating, for example. You might have some connections between these sectors, and then you have some constraints related to the logic of how they have to fit together. So it's also useful for allowing equilibrium systems that involve volumes, which are generally fractional values or could be fractional or continuous values combined with discrete values. So you might have some traffic, if we go back to that one, some traffic which is in volume, and then some very specific emergency vehicles. So it's a mixture of continuous and discrete. You can combine equilibrium problems with combinatorial optimization problems. We haven't done that yet, but that seems a lot harder to do. And you can also look at things like unit commitment in power and relax that and then add the constraints back in. We did that in this paper 10 with Richard Weinhold. You need some sort of push to push the integer aspects to come out correctly. So that's in the references, as you'll see. Okay, so where does all this fit in? Well, the big picture is the world is divided into convex problems and non-convex problems if we're talking about optimization. Left side is easy, in quotes. The right side is less easy. includes things like integer linear programs, optimal power flow problems, things that involve non-convex functions or sets. And once you have the physics involved, usually the right-hand side kicks in as non-convexity. And then that's the big picture. The bigger picture is that, well, if you can express optimality conditions for, say, convex programs, that's usually done via the KKT conditions, Karush-Kuhn-Tucker conditions, for nonlinear programs, which includes linear programs, convex quadratic programs, and many other problems. And so all those are special cases of this thing called complementarity problems, which is equilibrium, where it's not just one optimization problem. It might be multiple ones, each one interacting with each other. Like if you have a Nash-Cournot game, each player is solving an optimization problem, and there's some constraints or variables that are connecting them. Traffic equilibrium that I briefly mentioned, this is not even an optimization problem. It's just a set of conditions, the so-called Wardrop equilibrium conditions, that must be satisfied so that there's no incentive for people to choose different routes. There's problems in robotics. There's problems in mechanical engineering, where basically something is on, something is off. And that's the essence of complementarity. Something is, positive and the other thing is zero. So equilibrium or complementarity problems include optimization problems via their KKT conditions as a special case, and plus a whole bunch of other problems. So this is a really big class of problems, and there's some really interesting work the last, few decades. So we take that class of problems and we say, well, let's do an equilibrium problem. So we're in this space here, and then we add some integer restrictions. So we're looking at the intersection of integer programming and complementarity. That's basically where we sit. So let me give you an example that kind of motivates this a little bit more. So if you look at the classical transportation problem, we have a bunch of supply units, warehouses, let's say. We have a bunch of demand units, which might be cities. And then the costs are along the arcs. These are not the costs, but this is actually the answer. But you have a unit cost to go from warehouse 1 to city 1, or warehouse 1 to city 2, and so on, right? So basically, this is a well-known problem that's been studied for many, many years. But essentially, the primal variables are trying to look at the flows, which minimize the costs. And then the dual variables, the dual to the transportation problem, is these prices at each of the nodes. So either supply price or demand prices, and also called Lagrange multipliers, right? And what you'd like is to have these supply prices, for example, not just be numbers, fixed numbers, but to be responding to the flows. So they should be elastic, not fixed. And the same thing for the demand. The demand is not constant, it's a function of the prices. But this is the so-called catch-22 chicken versus the egg situation, where, like to know the optimal dual values, you need to have solved the optimal primal problem and vice versa. So which one do you do first? Well, one way to do that is to look at the Karush-Kuhn-Tucker optimality conditions, which will include necessarily conditions of this form that basically say the supply price plus the unit transportation cost. So this is the delivered price, has to be greater than or equal to the demand price, the price you're willing to pay. And if there's actually any flow, if xij, x being the primal flow variables, is positive, then this holds as an equality. Another way of looking at from economics is that if there's any activity between, say, node I and node j, so xij is positive, that marginal cost has to equal marginal benefit. So that kind of makes sense from an economics perspective. So here's on the left-hand side here, here's the more general version that says, let's let xij be the flow from supply I to demand j. And instead of fixed dual variables, now we have them as a function of the supply here being, for example, everything leaving node I, that's the supply at node I, and the demand is everything coming into node j if it's a destination node. So this is now a function, not a fixed value. And then we also have inverse demand function. And so the overall thing here is instead of these conditions, we generalize them to make them functions of the primal variable. So in fact, we have the inverse supply function as a function of all the flows out of that node I, plus the unit transportation cost minus the inverse demand function has to be greater than or equal to 0. That's a restatement of the other thing. And if xij, the flow, is positive, this thing has to hold as equality. And if this thing is strictly greater than 0, which means it's more expensive than the benefit you get, then the flow has to be 0. And that's given by this perpendicular operator, which says the product of those two things are 0. And so I basically stated what I just have here, that if the positive flow, this must hold as an equality, marginal cost equals marginal benefit. If this is actually strictly greater than 0, then no flow. And this is exactly a complementarity problem. One thing is non-negative, the other thing is non-negative, and their product is 0. So let's say we solve this, and I did that actually over here. And so what is the problem with this solution? Well, the problem is that warehouse number 4 has no activity. So if you're managing this network, this is a really bad use of this warehouse. People are just sitting there drinking coffee all day or something like that. So you would like to get some more equity in the solution to make supply node 4 active, not inactive. But we want to keep the equilibrium aspects, basically solving this problem here. How do you combine the equity enforcement with the equilibrium? Well, maybe there's one solution only, so you don't really have a choice. But if there's more than one solution, which might be the case, then pick from all those solutions the ones which involve warehouse 4. That's where the equity and the integer constraints example comes up. So for example, you might say, if the flow out of any particular node is less than some delta I, some contractual value, then force it, reroute things so that the flow out of node I is at least 25% of everything, of all the flows. So that's like a contractual requirement. These are obviously just arbitrary, but just to give you the idea. And in our particular example here, if you set the contractual limit here at 3, so if you drop below 3, which was definitely the case here because there's 0 coming out, then reroute things. And what it does, this is now the equilibrium solution, it just in a minor way changes it so that it takes 3 units from going from 1 to 2 and gives it to supply unit 4 now. So now it has 3, which is exactly the minimum here. So this is the type of thing you want to do. You want to take an equilibrium solution and reroute things in this particular setting for more equity distribution. Obviously, any sort of if-then constraints could also be applied, but this is a very specific one. Any questions on that so far before I proceed with the rest of the talk? I guess, Franklin, you've joined. Hi, Franklin. Okay, so complementarity problems. I haven't really explained them. Let me explain them here. So there's really 2 forms. I'll give you the more general form. It's called the mixed complementarity problem because you can have both non-negative and free variables. And it takes a vector valued function from Rn to Rn, 2 sets of variables, the non-negative ones, and then the free variables, and says for all the components related to the non-negative variables, you need a non-negative function, and then you need the product of these 2 things, the f and then the x is equal to 0. This is complementarity. And then for the free variables, you need a corresponding equation, right? So here's a specific example, just you can try this out on your own at home if you like. This has 2 x's and 1 y, and the f function is given by these 3 things, which are just linear in the variables. So x1 plus x2, x1 minus y1, and then the last one is also linear. And so the actual conditions you'd solve for are f1 non-negative, x non-negative, complementarity, same thing for f2, and then the third thing is f3 equals 0 and y equals free. And so here's one solution. Take x1 equals 0, x2 equals 2, and y equals 0. Are there any others? You can actually exhaustively figure this out in this case by just substituting away the y and then looking at the 4 cases for the x's, positive or 0, basically. So that's a small example, but just to reinforce this, that you've kind of seen this before if you haven't really seen complementarity. If you look at a linear program in standard form, and here it is over in 2, minimize C transpose X subject to these constraints, the corresponding dual problem is this one. And then we have this thing called complementary slackness, which is a kind of a same thing as complementarity. And it basically says if I have any slack in the primal constraints, slack is written as AX minus B, that times the dual variables has to equal 0, element by element. But since AX minus B is non-negative and Y is non-negative, you can write it as the inner product, which is the same as the element-wise complementarity. And that was primal complementary slackness. This is dual complementary slackness. So in fact, that's one example. And then in fact, if you wrote that out a little bit more carefully, you can rewrite linear programming primal and dual problem as a complementarity problem, where you have like the dual feasibility, complementary with the primal variables, primal complementary slackness, primal slack complementary with the dual variables, or you could write it out in terms of a matrix, and it would be basically, this is the F function involved. So the matrix here is what's called bisymmetric. It equals its negative transpose, and that's always positive semi-definite, so you can do interesting things with that. But anyway, linear programs, as a special case, are an example of a complementarity problem. So if you had 2 or 3 of these LPs together, the concatenation of them is also a complementarity problem. Same is true of over here, a nonlinear program, minimize f of x subject to these constraints. If you look at the Karush-Kuhn-Tucker optimality conditions, it's take the gradient with respect to x of the Lagrangian function, complementarity for the inequalities and the equations, put all that together, you'll get a function, the complementarity function, which is the first line of KKT minus gx is greater than or equal to 0, h of x equals 0. So it's basically taking into account at the same time the primal and dual variables. So that's the advantage from a modeling point of view. You can take into account at the same time primal and dual variables. It's very rich in terms of what you can do. Yeah, feel free to ask at any point if you have any questions. Okay, so that's a very quick detour through complementarity introduction. But let me go now to the meat of the talk, which is we want to look at this thing called the bounded mixed complementarity problem, which is to find a vector x so that, well, now x has, we're only talking about x's. The x's and y's are sort of merged together. The x's have a lower bound vector and an upper bound vector. So the lower bound could be 0 or it could be something different. And the upper bound could be whatever you like. These could also be plus or minus infinity. So the generalization of what I showed you before is to say, well, whenever x is at its lower limit, like it was 0 before, that the corresponding f has to be non-negative. If it's strictly between the upper and lower bound, the corresponding f has to be 0. That's like the y's in the previous example. And then what's new is that if it ever equals its upper bound, then you have to have the corresponding f to be non-positive. Before we didn't have any upper bound, it was just plus infinity. So this was never reached. But this is a slightly more general problem where we had upper and lower bound infinity and 0 for the non-negative variables, and then plus and minus infinity for the free variables. Okay, so this is the problem we're looking at. A special case is what we looked at before, spatial price equilibrium and so on. So what is the discretely constrained MCP, DC-MCP? It's basically let S be some subset of Rn, given subset of the variables in a bounded MCP as given above. Then the discretely constrained MCP is to find a solution to 11 such that all the variables in this set are integers. Okay, so integer and positive if they're positive variables, or just free variables, but integers. So some subset of the variables are integers is the idea here. And in most cases, S is integer valued or binary. And so, for example, there's many ways of doing that. You could actually create a function for if it's the binary variable. And the common trick is to take xi times 1 minus xi, and that thing has to equal 0. So that'd be like this case here. And then the solution of that, if you can find it, would be enforcing xi to be binary. And then you take the upper and lower bounds to be plus or minus infinity. So here, the function controls the binary aspect. You could also do more generally, if you want to have integers, you could say from m minus m1 to m2, you could look at the product of minus m1 minus xi all the way up to m2 minus xi equals 0. And the roots of that equation would, of course, be the integers that you want to hit, these integers here. And then you put a minus and plus infinity for the lower and upper bound. That's one way to do it. You can also add additional constraints on the continuous and integer value variables via some designated set X. I'll talk about that in the next slide. You can add auxiliary binary variables for the mixed integer nonlinear program formulation that I get. So there's many ways to have integer or binary restrictions on the equilibrium problem, basically. So let me talk a little bit about that. The cool thing here, at least from my perspective, is you have this function, the median function, that when you find the 0 of it, you've actually solved this bounded MCP. So here is the function, this H function. It's, again, we're trying to solve for x's only, right? That have these upper and lower bounds. It's xi minus the median, this mid thing means median, of the lower bound, the upper bound, and x minus f. And it turns out when you find the 0 of this function, you've actually solved these conditions. So I did not come up with this median function. This was from some work in the 1970s and maybe before, where they were looking at projection operators and trying to find the 0 of that associated function for the variational inequality problem. So this is like a specialization, if you will. But it does make you think, well, there's only several cases here, which of these 3 terms is the median, so that maybe you can do this with an integer programming type of thing, and that's exactly the first way we did it. So here's an example to make this clear. So we're taking the median of these 3 numbers, lower bound, upper bound, and x minus f, right? So if f1 and f2 are given as x plus y and y, and we have lower bounds and upper bounds given this way, then we just go through this definition, work it out in details here, and you'll see you'll get x minus the median of, well, the lower bound, upper bound, and x minus f of x, which is x plus y. That simplifies to x plus y if y is non-positive, x if y is positive. And then the second component here is the median of minus infinity plus infinity and y minus whatever this function is, which is y in this case, so you just get y. So it simplifies a little bit. And then if we look at remember we're trying to find the 0 of the H function. We look at the 1 norm of this vector, and we evaluate it at 0, x equals 0. It looks something like this blue kinked function. So in general, this median function, this one here that we're using, will be non-smooth. It's non-smooth right here at the origin, but it does give you some way to try and understand exactly how to find the 0 function relating to the original condition. So that's the whole idea here. And so how do we relate it to discretely constrained problems? We can solve an optimization problem which says minimize the vector norm of the H function, whose value should be 0 if we're there, and the variables x now we're looking at X and Y combined. The X's have to be non-negative. Some subset of them are non-negative and integer. Same for the Y's. They have to be, some subset is just real valued, and some are real valued integers. And then depending on the vector value norm that we use, then you'll get different problems. There might even be some additional considerations on the set X. Basically, any vector norm will do, but some are better from a computational point of view. And so then we get this, if we use the one norm, we get this a little more complicated expression where essentially what we're doing is we're creating new variables Z's and W's with positive and negative parts, and we're looking at the one norm of H. So it's the L1 norm of H that is being represented. There's a bunch of these constraints with new binary variables, the B's and the B tilde, those are binary variables, and they control which case we're in the median function, you know, because there's only a certain number of cases, right? And so for example, if BI equals 1, then, and M is a sufficiently large number, you get minus M, and Xi minus Fi minus Li is less than or equal to M times 1 minus 1, which is 0. So this says that Xi minus Fi is less than or equal to the lower bound, and it's greater than or equal to minus infinity. So that helps you with these three different cases that we're looking at, you know, which of these three things is the median. So without going through all the details, you know, and it's in the paper, you can just look at all these different conditions here with these two sets of binary variables that control all the cases of interest. And you can solve this problem, and that'll get you there. We'll see in a minute for the theorem. But you know, there are a lot of binary variables potentially, and if F is not linear, then this is a mixed integer nonlinear program. If F is linear, then it's a mixed integer program, a linear program. So this is easier to solve, right? Okay, so in principle, you could just solve this thing and be done with it, depending on the particular application that you're looking at, like the spatial price equilibrium or some other problem that you might want to look at. But you know, the computational details are a little bit to be determined. I should say that my co-authors on the second paper, they wanted to get rid of these binary variables to see if it was any quicker, and in some cases it is, but it really depends on the formulation and the solver choice together, which was interesting, I think, interesting insight. So I'll give you a little bit of a flavor of this continuous version, which is in the follow-up paper. Instead of so we're trying to recreate these conditions, the bounded mixed complementarity problem, right? So you can re-express that with a following set of inequalities. You can look at Xi minus Li times Fi, and that whole thing has to be less than or equal to 0. And then Ui minus Xi times Fi has to be greater than or equal to 0, and then X is between lower and upper bound. So these are, of course, these are non-convex inequalities because you have the product of variables and so on. But just re-expressing it symbolically like that, and this is sort of what we did. You could also add, if you had binary restrictions, you can add this sort of complementarity condition, which says that 1 minus Xi has to be non-negative, Xi is non-negative, and then complementarity, meaning the product of 1 minus Xi and Xi has to equal 0, which is another way of saying binary. So anyway, this is a continuous reformulation for, I'm calling this now the binary constrained MCP. And this condition is sort of what people use in two-level optimization called MPEX. They do a relaxation of that. In fact, the relaxation is instead of X times 1 minus X equals 0, it's less than or equal to epsilon. Then they let epsilon drop down to 0. That seems to work. This is the so-called regularization scheme of Schultes. And there's many other versions of this continuous one. We have a penalty version and several others, and we tried those in this second paper. This one is called the relaxed complementarity constrained problem, relapse epsilon, because of basically this thing right here. But let me move over now to some theoretical and numerical results. If there's any questions, just raise your hand. I guess there's a chat. Oh, somebody has to leave. Okay. So the first result, this is now going back to the binary constraint problem, basically says in words, it says, if you can solve this problem in the objective function, which was, as you might recall, the vector norm, the L1 norm of the H function, if you can solve that problem and it has a value of 0, then it's exactly solving the DC-MCP conditions that we wanted, which were these, basically, that you want to solve these conditions and have a subset of the variables to be integer. So that's kind of nice. That's the good news. It's if and only if. So if you solve this problem here, and this is positive as opposed to 0, that means there is no integer equilibrium solution. So that provides information as well. But if you manage to get the solution to have a 0 objective function value, then you're basically done. You solved it. And then all the other things are sort of housekeeping in terms of making sure it works out correctly. But that's the gist of it. And then what we did was we tried this on a variety of problems all the way up to 2,000 variables. And we tried to see if you could solve that problem, the mixed integer nonlinear program. And sometimes we knew there was an integer solution. So that's this column here. So this one, yes, by construction. Other ones we didn't know. And then we solved spatial price equilibrium, energy duopoly, and it seemed to work quite well for all these. In this follow-up paper, we did a much more numerical, extensive numerical set of experiments, and it turns out this particular binary version can be dominated numerically. It's quicker when you use the continuous version, but the right combination of solver and formulation makes a big difference, which I guess for non-convex problems is not anything new, but the insights here are relative to this class of problems. Yeah, so let me just summarize. Basically, this class of problems can apply integer restrictions to equilibrium settings. You get richer models. Allows autonomy in these infrastructure networks where people are solving separate optimization problems in terms of profit or time or travel, whatever. But then there's some sort of benign, benevolent, ruler here who's saying, well, we need some fairness as well. So that's where the logic constraints might come in. And so it's a more general way of looking at it is equilibrium problems combined with combinatorial optimization, generalizing the spatial price equilibrium example we had, and many other versions that are possible. So it's basically a lot of directions to go in, both theoretically and numerically. And I think you look at things where equity comes up, I think this might be quite helpful. Maybe faster ways to solve this if you need answers in real time, like for unit commitment problems and so on. But anyway, we have a few papers on this. There's 10 papers we're listing here. So these first two are with Franklin. I think you're in the audience, Franklin, and Miguel.
Yes, I am.
Hi, Franklin.
Hi, Steve.
Yeah, this was part of his postdoc from a few years back. And so we did some RLT approaches and other things, and applied it to traffic and power. This was the paper that earlier paper about the NESQ method, which is where you get the median function from, which came from another source before that. This was the paper, the main paper that I talked about. This is our book. We also had a few other papers where we looked at discretely constrained equilibrium problems, where we looked at a Pareto curve, trying to get integrality and complementarity traded off. So that was what we did in this paper with these co-authors. We also did it in this one. This is the new follow-up paper where we looked at more extensively at computational aspects. This was a paper where we looked, this was a number of years ago, also at the median function. And then this is the paper I mentioned. We looked at the unit commitment problem where you relax the binary conditions on the unit commitment, and you make them between 0 and 1, do the KKT conditions, and then add the binary restrictions after, which would be an example of DC-MCP. That's not enough to get the true equilibrium with integer constraints. You need to push it a little bit more with an upper level player, but there's some nice illustrations for the power market. So there's some papers here, other people have done some, but not a lot. I would say there's some work at looking at the integer linear complementarity problem, but not a lot of applications. So I think this is where, given that we're moving towards infrastructure and networks where the users have some autonomy, whether in traffic or energy flows of some sort, but then you want to also have a guarantee of some sort of equity. This could be a really interesting area, to pursue. So let me stop there, and that's the talk. Thank you very much, and see if there are any questions.